All right. Thanks. It's still 11:30. I would say. Good morning. How was the previous talk? Huh? Great. What do you mean great? Awesome. What do you mean by awesome? What means so far so good? Informative. Okay, fine. Yeah. Okay. Now, since what did you all come here for? Only building a telescope and going with it. And learning about the telescope, isn't it? Using your telescope, learning about it, how the telescope works, isn't it? Right? So, before we assemble or start building the telescope, we will understand everything that there is to know about your telescope. All right? That is the telescope you are going to be assembling. Okay? That is the telescope you are going to be assembling. Yeah, that telescope is like this smaller. Here there is a person standing next to it. See how big it is. I could have shown you. Okay, yeah, fine. Now, before we assemble everything, can someone in the group here explain to me or describe to me what a telescope is? Guhan and his notes.
Like a telescope, like if you point it to a celestial body, it like zooms it in so that we can have a clear vision about it.
Okay, zooms it in and have a clear vision about it, isn't it?
Yeah.
You know, you are familiar with the new S24 Ultra, S25, isn't it? Yeah, so that can also zoom into the moon and says, that's what they say. Is that a telescope then?
Telescope is a tool with the help of lenses and mirrors. It magnifies the light coming from an object so that we can obtain a more clear view about
Wonderful, yes. It magnifies whatever you're looking at, isn't it? Okay. Since we are, yeah, okay, go on.
So, telescope is basically a device which helps you to see things which your naked eye can't.
Naked eye can't.
Like, can but very small.
Okay,
It
fine.
basically magnifies.
Previous talk talked about radio waves or radio spectrum and the X-ray spectrum, isn't it? Can your eye see that? No. Can your telescope see that? Can your telescope see that? No. What does your telescope see? Optical. Now, when you look at night sky, can you see the stars? Considering clear skies, not in Bangalore though. And when you can you see Jupiter? Yes. Can you see Saturn? What about Uranus and Neptune? You can't? Sure. Rare situations, yes. You have seen through your naked eye. Where was this? Not, most probably not here. Not in the city, right? Not you, man. Behind you, there is one more person. Okay, fine. See, telescope is an instrument, see, like tools that helps us to see far, far away things magnified, or basically whatever object that you look through a telescope appears magnified to us. Is it actually magnified? Or is it actually increasing in size? No. It appears. Now you also learnt about apparent magnitude and absolute magnitude, isn't it? So, apparent magnitude is how bright the star appears to us. It matters. It appears big, but not actually that big, right? So, a telescope uses lenses or other times mirrors to help us observe far away objects magnified, all right? Now, today we will be discussing about your telescope, what you are going to make. Now, considering telescopes, there are two types, mainly two types. There are other sub-classifications also. But the main two types are reflecting telescopes, okay, and refracting telescopes. Can anyone tell me the difference between a reflecting and a refracting telescope? Anyone? Very good. Splitting of light, is it? The way light bends, isn't it? Where? Does light bend here? When it changes medium, right? Refraction is basically the bending of light or the slowing down of light when it enters a different medium. For example, in our case, you can have a lighter medium, which is air, and a denser medium, which is glass, normally glass. All right. Even water can refract light. A prism also refracts light, but it splits it into different colors, right? What about a reflecting telescope? It reflects the light. Good. How can light being reflected make the objects bigger? Thavanish, wait. I'll ask. Hitesh. Yeah, you are sitting cozy there. How do you think light bouncing off of reflective surfaces make objects bigger? Why did I have to sit in front? Say, man, try. It's okay. Say. No, you were, yeah. With the use of concave and convex mirrors. Now, does that happen in refractions also? Sure. Pranav, right? Pranav, why do you have specs? How much can you zoom in through your specs, man? Little bit. Okay, fine. What is on the specs? What do they use to make it? Mirror, lens, glass, lenses, isn't it? Now, when you look about a lens is basically a piece of glass, okay, that is structured in a way that it is able to bend light in a particular angle, okay, and all that angle depends on the refraction, how light refracts off that lens, and also how the lens is structured. All right, this helps the lenses to magnify objects. See, as you can see here, in a refractor telescope, you see a lens here. This is known as a convex lens. Okay, so you see A to B. Imagine that is Jeffrey standing there. Now, this for your information, that is Jeffrey. Okay, wave. So imagine this is Jeffrey standing there. Okay, and light is hitting off Jeffrey and reflecting all the way in parallel lines through or to the lens, convex lens. Now, convex lens is basically when the lens is bulged outside or outwards. Okay, so what happens is because of this bulging here, the structure of this lens, the light basically bends, and you can see that all the light rays are being focused onto one point here. Right? Right? This is what you call the focus or focal point or focal length of the lens. Whatever light comes, all the light rays focus right here. Now, if I ask you, can you see Jeffrey in this point? What will you say? Yes. Okay. How will Jeffrey look? Inverted. Then? Huh? Could be a real image. Oh, you know about real images, virtual images? Okay. Can you see Jeffrey here at this point as Jeffrey looks at this point? No. Where can you see Jeffrey at the same length and distance? Before the lens or after the lens? Okay. What if you see before the lens? What happens? How will Jeffrey look? The same. What about after the lens? You look upside down, inverted, isn't it? Why does that happen? See, as you can see here, see A, look at light ray A, it is going and it's refracting and hitting the focus and coming down. Initially the light was on top portion, now it has come to the bottom. So where Jeffrey's head is, here Jeffrey's legs will be there, right? Of course, all the floor behind, underneath him. But this is how basically a refractor telescope works, basically based on refraction. Okay. Now, the earliest telescope, the one made by Galileo, of course, you may have the assumption that Galileo invented the telescope. Yes. How many of you think here that Galileo invented the telescope? No. Choose your words carefully. How many of you believe that Galileo invented the telescope? Just because I asked the question like this, you are lowering your hands now. They are guessing like it should be wrong. Okay, now. Popular science or history of science says Galileo is the inventor of the telescope. But let's say he is not. There was this person who always used to make specs, or specs that you use, okay, named Hans Lippershey. Hans Lippershey. He used to make these lenses for specs, and suddenly on an accidentally he saw that when you arrange certain lenses in one particular orientation or just back to back, he saw that some objects appeared which are far away, or some objects appeared magnified or closer to him. The only problem is he didn't use that to see anything outside. He didn't use it. He accidentally discovered one of the greatest instruments mankind has ever seen, but he didn't use it. It was later then Galileo used it for astronomical observations, and Galileo became famous when he discovered all the 4 moons of Jupiter. Okay. Also, he observed the craters on the moon and everything. All right. Remember, Galileo did not invent. He used, or one of the first people to use the telescope for astronomical purposes. That was a refracting telescope. He used lenses. Now, refracting telescopes are very easy to make. For example, you have a couple of lenses, a convex lens and a concave lens, okay, and that's it. You can make a refractive lens. Yes. Huh? No. It is easy to make because a couple of lenses can give you a refractor telescope. The problem with a refractor telescope, now see, if you see this image here down, the second one, okay, say the lens extends all the way till here, okay. Now if I draw a line, okay, I'll just show it to you. Imagine if I draw a line from here to here and just cut this portion off, the outer edge of the lens, right? What shape is it in? Only the outer edge from here to here. What shape? Triangle. What is another object that is made out of glass? Exactly. That is also a triangular shape, isn't it? What happens when a light ray enters a prism? It splits. Yes, it splits the light into what? 7 different colors. Wonderful. So, do you think the same thing will happen here? The same thing can happen here? Yes. So, one of the main problems with refractor telescopes where you use lenses is when you can have something known as chromatic aberration. Chromatic aberration is basically the edge of the lens, okay, refracting or splitting the light into several colors. You see here, right? Now, when you look at some object, say the moon or Jupiter, do you want Jupiter's image to appear red, blue, green, or do you want the actual colors of Jupiter? So, if you use this, okay, the problem is that sometimes when the lenses get bigger, the objects appear to be split into the several colors. So, you'll have multiple images or maybe a ring of red, blue and green around the image. This is one of the main issues with a refractor telescope where you use lenses. The other issues include, okay, making lenses is hard. You have to be clear about the lens. The lens should be clear, okay. Making those lenses are very difficult. It is expensive. And as bigger as they get, the more difficult it is. You have to handle the lens, right? Imagine this big lens. It's very difficult to handle, it's very difficult to make, right? So these are the problems with such refractor telescopes. So that is when, okay, of course Galileo used a refractor telescope, a very small one, or not a very small one, but still. And he used that to observe Jupiter and everything. But as it got bigger, people started noticing these issues. That is when one person, okay, he was born on December 25th, okay, December 25th, and when he was around somewhere around 30 years of age, okay, he transformed the entire civilization. Who is that? Wonderful. Nobody said. Exactly. So what Isaac Newton, the founder or discoverer of gravity or formulation of gravity, he did was basically modified Galileo's design of the telescope, and instead of lenses, he used mirrors. Now, not just any mirror. Uh, what type of mirror is this? How many for concave? How many for convex? Okay. In the case of mirrors, okay, the one that is bulging inwards where the reflective surface is, that is what you call a concave mirror. Whatever bulges inward is a concave, whatever bulges outwards is a convex. Understood? Okay, fine. He modified the refractor telescope, and instead of lenses, he put mirrors. Now, you all have mirrors in your home, right? Do you look at yourself in the mirror? And what do you see? Yourself. Do you see yourself enlarged? Do you see yourself diminished or smaller? You appear as if you are there itself, isn't it? However you are, you appear like that only. Right? Right? Why is that? Sriniti. Oh, everyone will get a chance. Don't worry. This time you. Hi. Why do you appear as you are in your mirror, the home one? Wait a minute. I am asking you. It's a plane mirror. What is a plane mirror? You inverted, Laterally inverted. Fine. Do you appear as you are, the size, the shape, everything? Good. Why is that? Flat. It's fully flat, isn't it? It's a plane mirror, right? What happens to a plane mirror when light hits its surface and reflects off of it? The light bounces off. In what angle? At the same angle it hit the. So imagine the light is going from here, and instead of this, if it was a plane mirror, what happens is the light will just simply bounce off back, right? What you get is, what you see is what you get, that's it. All right? But when you slightly bend the mirror, add a small curve to the mirror, what happens is light actually bends. So in the angle that you are curving it, okay? For example, see, this light ray is going, okay, and hits the mirror, and since the mirror is curved, you can see that the light is reflecting off in a different angle. Same thing here, and where does it reach? What is point F? Focus, right? Same as in the lens, you also have a focal point. Now, such a concave mirror basically makes the object appear larger than it actually is. Yes.
Now, please pay clear attention about whatever formulas that they are teaching and whatever Tony sir is teaching, because the mirrors that we are going to give you guys is not of fixed focal length, is about varied focal length. You can get F6, you can get F8, you can get F10. It is up to your luck. So, when you are, if I say, kindly fix your secondary mirror at some X of the focal point, you guys should be able to do all that. So, unlike the last time, there will be no ready-made things to be given. That is why I said it is a 2 days intense. So, nothing ready-made. You guys have to cut the wood. You guys have to. Yes, stand. How do you think you will be doing the Dr. Nirma?
Yeah, we are.
We are.
See, you learn a lot of things like carpentry also.
There will be carpentry job as well. No, no, no. There's no welding. No, 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 no. Yeah, you can.
Depends.
Okay. Yeah.
Okay, fine.
So this is the base of the optics. Let me be very clear. So if you guys are expertised in this, the next journey will be very easy. Okay? Yeah.
Okay. So you see that the image appears at the focus. And how will the image appear on a screen? Is it a real or a virtual image? Is it inverted? It's a real image, good. And is it inverted? Is it lateral or straight? Laterally inverted, or it's inverted, upside down, isn't it? Why is that? Once again? Very good. So this is how a reflecting telescope, or basically concave mirrors, work. Now, instead of a lens, what Newton did was he kept a basically a concave mirror, okay, at the very base of the telescope, okay, and he made all the light reflect off of this telescope to focus at one single point. And instead of this point, he kept another mirror, a flat mirror, basically to reflect off the light at a 90-degree angle. Okay, the light will reflect off a 90-degree angle, so that you can view it somewhere around here. You can view whatever you are seeing somewhere around this area. All right, that is how a reflecting telescope works. The advantages of a reflecting telescope over a refractor is that, see, since there is no splitting of light happening here, okay, you don't get to see images appearing red, blue, green, all the other colors. There is no chromatic aberration basically, right? That is fixed. Making mirrors is a simpler task than making lenses, right? All right, good. So that is how basically a reflecting telescope works. Now let's look at the parts of a telescope. Okay, it's not just a mirror kept somewhere and you are looking at it or anything. You have a lot of things going on the telescope. So first one is the objective, the lens or the mirror. In both refracting or reflecting, you will have one primary mirror or lens that is kept to focus or capture all the light and focus it to one single point. In the case of refractor, it was a convex lens. In the case of reflector, it was a concave mirror. Good. Now, the objective or the primary component that gathers light, in a refracting telescope, this is the objective lens. This is the primary mirror in the reflecting telescope. Next comes the eyepiece. Now, it's not like you can take a telescope and you can project it somewhere. You have to see the object yourself, isn't it? And you need something to see in it, right? For example, in that camera, okay, you always see that people see through one small hole, isn't it? Right? Much like that, the telescope also requires one particular object or component, that is the eyepiece. Now, eyepiece is a lens that basically magnifies the image. It is not exactly, or it is not only based on the primary mirror or the objective, okay? It depends also on the eyepiece that you use, okay? Fine. The next is the tube. You saw in the image that there is a huge tube, isn't it? Right? That is known as the optical telescope assembly in the case of optical telescopes, okay? The mount is where you keep the optical or OTA or optical telescope assembly, okay? And there are very different types of mounts. The one you are going to build is what you call a Dobsonian mount. Now, in the case of a Dobsonian mount, it is one of the simplest mounts that you can use. What you have is, you have a sideways motion and you can tilt the telescope up and down or in this angle, right? That's it. That's a Dobsonian mount. It is one of the simplest and most widely used. And it's also easier to carry and everything, yes. The other types are equatorial mounts and all-azimuth mounts. Now, equatorial mounts are designed for tracking celestial objects as Earth moves. Now, see, when you are using a Dobsonian mount, you know that the Earth rotates, isn't it? When the Earth rotates, objects also tend to move in the sky, right? Now, imagine you are focusing at something like Jupiter. Jupiter is very far away and the Earth is rotating at a very high speed also, right? Do you think that Jupiter will move out of view very quickly? Yes? So, how do you keep it focused on that Jupiter itself? So, see, Jupiter is here. You can see somewhere in this area, okay? You might see Jupiter as a dot here, okay? And quickly it will just go like this. Done. And after that, you will have to correct the telescope, adjust it once again. And by the time you adjust it, it will just go again. By the time you keep the next adjustment, it will just go again. Alright, this happens. And you can't keep on adjusting the telescope all the time, isn't it? Especially for astrophotographers who like to photograph these magnificent objects, okay? You use long exposure photographs where you keep the camera on, shutter on for a long time. And if you keep the shutter on for a long time and the object moves like this, can you capture it? No. So what you do is you have mounts that are designed or aligned with the equator of the Earth, okay, so that it just moves along as the Earth rotates. If you point it at one object, it stays in that one object. Of course, there are corrections that are to be done, but much better option for astrophotographers or long researchers than a Dobsonian telescope. Ultra-azimuth mounts also work in a similar way. Now, a focuser is basically a mechanism that allows the user to adjust the position of the eyepiece for a sharp image. Basically, see, you have the eyepiece kept at one particular distance, okay? And sometimes you might see that the object or image is not very focused, it will be blurry, okay? And you have to adjust it, fine tune it, you have to move the eyepiece, you have to bring it back or something. But even after that, sometimes it might not be possible. That is why you keep an additional lens, okay, a particular focuser to focus that light even further, all right? And a finder scope. You've seen, okay, how many of you play shooting games? I don't. Okay, you have those guns where you have the scope. Why do you use the scope? Aim it, isn't it? A finder scope is basically the same thing. Instead of shooting people, you point it at astronomical objects, okay? It helps you point to that object or direct to that object. Okay, let's talk a little bit about eyepieces. Again, eyepiece is something that helps you focus or view the object magnified, all right? It is a critical component because without the eyepiece, you cannot see that object magnified or anything, all right? Now, the one particular or important fact about eyepiece is that it determines the magnification. Now, for example, you have a particular mirror, okay, at a particular focal length, all right? And do you think that focal length can change? Do you think the focal length can change? Yes? No or yes? Yes. How many say no? How many say yes? What about you three? Look, the mirror in your homes, does it change focal length? Maybe at times you appear bigger, at times you appear smaller. No. It's fixed, right? Similar to that, whatever you get, the focal length of a mirror, the primary mirror or the objective in a telescope is fixed. If you want to change it, you have to disassemble the telescope, entire mirror and put another one. But that will also take a lot of procedures. We have to change all the other values. Now, you want to see an object, for example, the moon, okay? You are observing the moon. You see it magnified, wonderful. But you want it to magnify further. You wanted to see it magnified even further, even big. You want to see the individual craters on the moon. You can't change the focal length of the objective, the primary mirror that we are keeping. So what do? You change the eyepiece. So the eyepiece determines the magnification of the telescope. Now in this section you see a field of view. What do you mean by field of view? The area you can see with? I am only talking about field of view in general. The area you can see with, or area you can see, that's it? Good. Now, field of view is basically the area you can see, and in the case of an eyepiece, the area of the sky you can see inside or through the eyepiece. That also depends. Now, for example, come over here. Okay, Guhan, come. Never see you again. Why your fighting is not over? Okay, Guhan, go there and stand. How do you see me? Same. I didn't want you to see me magnified or anything. Okay, can you see whatever is behind me? Yeah. Yes, come closer, little bit closer. Can you still see whatever is behind me?
Yes, but not as.
Not as that much, right? Do I appear magnified? Little bit. Come closer. What do you see?
So only one little bit back.
Louder, man. Let them also hear.
Only sir and little bit.
You are not like this in the classroom, no? You are so loud in the classroom. Now, what happened? Okay, well, listen. Yeah. Yes. What happens? When you come closer again.
You can only see you.
You can only see me, isn't it? Now, the magnified, are you looked magnified than before? Yes. But when the magnification increased, can you see everything else?
No.
It slowly decreased, isn't it?
Yes.
Thank you. Good. Okay.
Tell the details, man. We all do in this field.
Now, as magnification increased, yes, you are seeing, of course, so more details of me. Don't tell. Okay? Much more defined, yes. But at the same time, what happened? What? This is what happens in every classroom. So, as the magnification increased, of course, the details, what Guhan saw of me also increased, more defined. But at the same time, you see that the field of view, whatever Guhan was seeing apart from me, also slowly decreased. All right. As you get closer to the object, whatever is behind or around the object seems to get less and less. So when you magnify something, the more you magnify, basically the less of everything else you see. Not that object, but less of everything else that you see. All right, which is very important when using your telescopes, because if you are using it to see the moon, in order to see the moon, you will see that there was a telescope here, man. Where is it? Okay, fine. In order to see the moon, you will see it as it is a full moon. Yes, you will see some of it around also, the stars around it also. But when you want to magnify it, forget the stars, only the moon is visible. When you want to magnify it further, okay, you can see the individual craters, but nothing else. All right. It all depends on what you want to observe. Do you want to see the moon as a whole, or do you want to see moon detailed, highly detailed, but less of everything else? That depends on you. Okay. Now, the eyepiece, since the eyepiece is a lens. Okay, have you used microscopes? Yes? No? How many use microscopes? Okay. You look through something, right? Exactly. That is also an eyepiece only. The same thing. Yes, you need that. So basically the eyepiece is also a lens. Okay. Whatever light is coming from the primary mirror, okay, which is reflected off of the secondary or that flat mirror, okay, it comes at an angle and you have to focus that light, okay, in order to magnify it. So it features a lens, very small lenses, and it has shorter focal lengths. Now, the telescope you will be getting, of course, as sir mentioned, very different focal lengths. Okay, your luck what you get. Anyways, the telescope mirror that you get one of them has a 92 centimeters focal length. So that means an object, let's say Shravan sir is there. When I try to view him or magnify him, the image will be focused, the image of Shravan will be focused 92 centimeters away. Exactly 92 centimeters away. All right? Understood that much? Yes? Now, in the case of eyepieces, you will have very shorter focal lengths. For example, you will have a focal length of around 25 millimeters. Very small. All right. That is how it magnifies, which you will learn how. You will be doing all the calculations after by while. So shorter focal lengths, let's say the less focal or lesser the focal length you go, as you saw here, when Guhan came closer to me, okay, the magnification increased. When Guhan went away from me, the magnification decreased. The field of view increased, magnification decreased. Shorter focal lengths will give you more magnification, less field of view. All right, fine, understood? Good. There are different types of eyepieces. All right. Kellner, of course, is the name of a person. Like we always learn in astronomy, everything is named after a person. So Kellner is a type of eyepiece. Okay. Flosel is a type of eyepiece, and also there is one more type of additional component that we give to an eyepiece to increase its magnification, known as Birla. Anyways, Kellner is a 3-element lens system, which means that there are 3 lenses in the system or in the Kellner eyepiece. Okay, so and Kellner eyepieces are very inexpensive, not very expensive, very cheap, and it is good for beginners like us. We are all beginners in astronomy, amateurs. Yes, you are asking something. So why did you do this? Okay. Kellner eyepieces are inexpensive. They are lightweight. They are cheaper. Okay, they use 3 lenses. All right, and in the case of a Flosel eyepiece, you have a better eyepiece, or basically all the components that you use are better than a Kellner one. Okay, it is for somewhat advanced level of astronomy. Okay, and it has a 4-element symmetrical design, 4-element or 4 lenses inside the Flosel lens. And one thing that you have to understand about a Kellner and a Flosel is that the field of view varies very drastically. So for example, in a Kellner eyepiece, you might have somewhere around 48 degrees of field of view. 48 degrees, all right? But as you go to a Flosel eyepiece, it can vary till 50 to 55 degrees, which is better because you can see more of the sky, all right? So each eyepiece will have its own different field of views, and it all depends on what you want. In the end, everything depends on what you want to observe. Do you want to observe the moon? Okay, or do you want to observe some deep sky objects like Andromeda galaxy or something, right? Galaxy, no need moon. Start with the moon, then you go into galaxies. Okay, now something you have to understand about eyepieces is that eye relief. See, when you use microscopes, whoever people use microscopes, you have to look through that very small opening in the eyepiece, isn't it? Very small opening, right? And as the magnification increases, that opening also gets smaller and smaller, and it is very difficult. It becomes very difficult for you to observe it through that small opening. Okay, that is what you call the eye relief. Basically, the easier it is, or how easy it is for you to look through that eyepiece. Okay, now Flosel eyepieces, okay, as the magnification increases, the eye relief basically reduces, which means it becomes more difficult for you to observe. What you will be getting is something known as a 25 mm eyepiece, which is very much enough to observe Jupiter and Moon, also Saturn. Fine? Good. I had someone here. Yes, talking about eyepieces again, wide field eyepieces. Now, wide field eyepieces do not focus much on magnification. It focuses on wide field of views. So it can get up to 68 or up to 88 degrees of field of views. This is important for deep sky objects like Andromeda galaxies or observing galaxies in clusters, because they are so vast. Unlike the moon, they are extremely vast. Okay, they cover up a large part of the sky, so you have to see all of them. If you use a shorter focal length or a highly magnified eyepiece, you cannot see all of them. You'll see a part of it, but that is not what you want. You need the entire galaxy in view, right? So wide field eyepieces help see deep sky objects, not magnify, but more of the sky. Of course, I mentioned Birla lenses. Okay, this is not an eyepiece. Basically, it's an accessory. Now, for example, you have an eyepiece which gives you or let's say whatever you're looking at is magnified 36 times. Okay, a Barlow lens, say it has different types. What I want is you want it more magnified. So in order to get it more magnified, you have to change the eyepiece, right? Go a shorter focal length. The problem is you only have money to buy one focal length, one eyepiece. So what do? You have to shorten the focal length of the eyepiece or increase the magnification of the eyepiece without buying another eyepiece on its own, because eyepieces are expensive, right? Then you use a particular lens or accessory known as a Barlow lens. What it does is basically increases the focal length of your increases the magnification of your existing eyepiece. You have 2x or 3x. So for example, if you have a 36x or 36 times magnified or magnifying eyepiece, what a 2x Barlow will do is basically magnify it 72 times. All right, 3x, 3 times that. It's an accessory. All right. Now, next. Focal length. Let's now get into a little bit of math. This is very important. Okay. Not now. This is important. The focal length is the distance between the center of the mirror and the focal point, as you have seen before, right? The focal point lies somewhere here. All right. So, how do you calculate this focal point, or how do you calculate it? Suppose you have given a mirror or a lens. How do you calculate this? This is one of the very important equations or formulas in optics. This is called as the mirror formula. It is basically to calculate the focal length of a mirror. Now, if you want to understand what is all these objects, this is the object distance. The object distance is basically the object. So, for example, if it is Jeffrey there, or Kritesh, or Thavnesh, he is the object. Okay, imagine the object is placed here, all right, and the mirror is placed over there, where the pointer is. All right, the object distance is the distance from this mirror, the objective, to the object, whoever it is, whatever it is. All right, and the image distance. Now, the image distance, what do you mean by image distance? What image? Image form, projected image. Good. Now, depending on the mirror, okay, it might form anywhere in between this. All right. So, basically, imagine if the image is formed somewhere here. All right. This becomes the image distance. Now, mind you that the image should appear. How will it appear? Real or virtual or inverted? Virtual or inverted? In case of a concave mirror. Inverted. Then real? Real. Good. Imagine, okay, keep in mind that the image should have the same dimensions as the object. Okay. So, that becomes the image distance. Now, when you do this calculation, 1 by f basically, or f is the focal length. If you do this calculation, what you get is where the image is focused, or where the focal point of the image is, or the mirror is. Fine. Note it down quickly. Now, you will be doing this, measuring the focal length of the mirror, okay, soon. All right. Don't have time. Okay, this was for you to measure the focal length, but we will do it next. Wait. Move back. Yes. After you found the focal length of the mirror, okay, you have all the other parameters to find, which is magnification, a value known as focal ratio. You heard sir mentioned f8, f10, f6, f5, all those things, right? That is focal ratio. The field of view, how much you can see, that also depends on the eyepiece. The resolution. Now, what do you mean by resolution? The quality of the image. Any other answers? how clear the image is. Any other answer? Those who play games. How many pixels? Okay. You have seen that 1920, 1080, 1080p, 2160p. P resolution, right? Exactly. So now think of it like this. Okay. Imagine both of you, okay, are standing very far away, say at least 1 kilometers away or 1.5 kilometer away. How would they appear to you? A dot, tiny. Can you distinguish between both of them? No. But as they get closer, can you distinguish between two of them? You can identify that there are two people standing, isn't it? But when they get far away, it becomes almost close to one, right? Basically, the resolution is how defined or how distinctly you can see two objects at a distance, all right? And there is a limit to this resolution. Fine, that you have to calculate, because aperture is basically the size of the mirror or the diameter of the mirror that you are seeing, and brightness. Okay, next. Okay, now take out your weapons, calculators, distribute. Yes. Okay, in front of you, we are giving you a worksheet, okay, to calculate all these parameters. In that worksheet, you will find all the formulas written. Is it written right? You didn't write it? I have to mention it. Give me one. Okay, you will not find all the formulas written. I'll mention it to you.
Ask them to guess if they can.
Is it there in the PPT?
This.
Formula is there. No, I will not use the PPT. Can you? There, I'll tell you, man. Wait, I'll tell you. Wait for the instructions, no? Did everyone get the worksheets? Is anyone left? No, right? Okay. Read the first page, first and second pages. First two pages. I have to wind up quickly. It's 12:30. Okay. Of course, you have to write. No need. It's okay. Class is fine. We know your names. We know where you're coming from. So, in the worksheet, you have something known as prerequisites, which meaning you need to have basic mathematics skills with ratios. Ratios meaning fractions, proportions, also fractions. Understanding log, which I believe I have taught you before. We have come across before. Logarithms. Yes? You know that absolute magnitudes require logarithms, right? And angular measurements. You also came across degrees, arc minutes, arc seconds, parsec, all those things, right? So you are well equipped. Then I don't have to do anything. You can calculate yourself, no? Okay, fine. Now, in the second page, What is the black hole? Where?
Black hole. Board.
Blackboard. What does it look like? Green, eh? Yes. See, olden days you had blackboards. Since this institution is very old, you will have blackboards. In my opinion, blackboards are better. Okay. We'll see that after all the description is done, okay, you will see let's find out, a session called let's find out. Next page. Let's find out. Got it? Right? Yeah? Understood? Good. Now, we will be dealing with mostly millimeters in this session. Okay? Not meters, not kilometers, mostly millimeters. Somewhere or the other along the way you will find centimeters also. Okay? Just bear with it. Now, the first thing that I want you to do is magnification. Find out how magnified an object will appear. And for magnification, there is a formula. So, we write magnification as M, of course, first letter comes. And in order to find the magnification, all you have to do is, okay, find out what the focal length of the objective or primary mirror is, which we will write as FO, focal length of the primary mirror or objective. And I remember I told you the eyepiece determines how magnified the object is. So, shorter focal length which will give you higher magnification, longer focal length will give you lower magnification. And what about the field of view? Very good. So, comes FO belongs to the objective or the primary mirror, FE the focal length of the eyepiece. Alright. Now, once you are done with that formula, you will see that in the next page you have two questions, two scenarios. Read the first one, someone. Someone, yeah. Go ahead and read. Wonderful.
A telescope has a focal length of 1200 millimeter and
Mhm.
an eyepiece with focal length of 25 millimeter. Calculate the magnitude.
Very good. Now you have a telescope, or the objective of the telescope has a 1200 millimeter focal length, right? And the eyepiece is of 25 millimeters. Okay. What it asks you to do is calculate the magnification, which I assume is pretty simple, because you have all the values that you need. So I suggest you go on calculating quick. I don't know. Is that it? Use your calculator. This you don't need calculator also. This is very simple. So what do you have to do? What is the ratio that comes? Or how does it? What is the step? Okay. 25 mm it is, no? So, right? Good. 48x. What do you mean by 48x? Wait, what? Very good. 48x. 1200 by 25. Alright? Which means the object appears 48 times its actual size through the naked eye. Alright? This I have told you. Next question. Read the next question, please. Sonakshi. Okay, read.
50x and the eyepiece focal length is 20 millimeter. What is the focal length of the telescope?
Now what do you do here? It's easy, yes. So do.
Sir, focal length of eyepiece into magnification.
Focal length of eyepiece into magnification.
100.
So what do you get? 100. 100? 100 times. What did I ask you to find there?
100 millimeter.
Wonderful. 100 millimeters. Always remember the units. Right? Always remember the units. If I tell you 100, what 100? 100 kilometers, 100 kg. No, I tell you 100 millimeters is the focal length, which means the mirror's image is focused 10 centimeters after it or in front of it. Alright? Now you are done with focal length or magnification, right? Good. Let's switch to field of view. Remind me again, what's the field of view? Very good. Area of what? Area of what? The object. The area of what? Surrounding. Surrounding means this. You mean this surrounding? Where are you pointing at with the telescope? Are you pointing at your house? Your particular object. Where is that object? Where is the object? In the sky. The area of sky that you can see. That is field of view. Now, for field of view, calculating field of view, you have, okay, we take it as field of view, FOV. Now, for calculating the field of view, one important thing is the eyepiece itself. Remember once again, the magnification. Remember once again, as the magnification increases, the field of view reduces. Magnification decreases, the field of view increases. So it all depends on the eyepiece. Now, to calculate this, you have to calculate or measure the focal length of the, field of view of the eyepiece, and since it is tied or related to the magnification, FOV of the eyepiece by the magnification. Alright? FOV field of view E of the eyepiece. Okay? Now, first question, anyone? Good. The eyepiece has an apparent field of view of 68 degrees and the telescope has a magnification of 40x. Calculate the field of view, which I assume should be simple. Field of view is basically you are pointing at somewhere, right? Imagine you are seeing this much part of the sky. Okay? This itself is the field of view. Alright? In this, the moon will appear somewhat like this. But if you want it more magnified, it will appear somewhat like this, which means the field of view is reduced. Right? That's all. Now, in order to find field of view, all you have to do is take the field of view of the eyepiece and divide it by magnification. 68 by 40. 1.4 what? Kilometer. Degrees. 1.4 degrees. Now, say, why is it measured in degrees? Now listen, take your eye for example. You can see from this point all the way to this point. What angle does this make? 180 degrees, right? Now since your eyes can move like this, you have an effective field of view of 180 degrees. Okay, it's actually more, but still you can have this. In the sky, you also measure areas in terms of angles or degrees. Alright, so 1.4 degrees means that 1.4 degrees in the sky will be visible to you. Alright, now giving that, okay, the moon 1.7 it is, fine. Hey. Okay, 1.7, yes. Okay, now I'll tell you the moon is only, or the width of the moon is only 0.5 degrees. Can the moon fit in this 1.7 degree field of view? Yes, because it is less, right? Right? Say you have this field of view to be 1.7 degrees, alright? And the moon is only 0.5, which means that is only this much, right? Which means it will fit in. But in the case of, let's say, a galaxy, somewhere close to 3.7 degrees, will it fit in this? No. So what should you do? Increase the field of view. So increasing the field of view, what should you do? Exactly. So increasing the field of view of eyepiece, what should you do? Reduce the magnification. Wonderful. Yes. Now, next comes resolving power. Resolving power is the smallest separation between two objects. Basically, what I explained before. Can you distinguish between two objects? That is what you mean by resolving power of the telescope. Now, the equation for that or the formula for that goes like, we take resolving power as PR, power, okay, and now what is this 138? Yes, oh. What is this 138? You all remember Vinayak sir? Yes. What is 138? Now, when you were listening to the talk about RRI and cvraman, right? You heard about or you saw one diagram about Rayleigh scattering. Yes? Yes? Something related to that, which I will explain later, okay? So, to find resolving power, all you have to do is divide 138 by the magnification. So, first question, I'll tell you. Because if I go explaining 138, okay, it will keep on extending. The time is still 12:30. So, first question. Fast. Mm-hmm. Very good. A telescope with a 200 mm aperture, find its resolving power. Yes. Pushpita ma'am. Shouldn't it be 138 by D? 138 by D. So the question is resolving power. Should be D, right? Okay. Listen, please. It's actually not magnification, it is the diameter of the mirror. So you see that aperture, isn't it? 200 mm. Right? 200 mm is the diameter of the mirror. 200 mm means 20 centimeters. Right? So 138 by D. Now what you have to do is divide 138 by 200. What do you get? What? 0.69. Is it 0.69? Good. In what? What will be the unit? Millimeter. Vinayak sir will say. Has to be arc seconds. Okay. Now, what this basically does is, this is in arc seconds, yes. What it does is, if the objects are separated by a minimum distance of 6 or 0.69 arc seconds in the sky, okay, you will be able to see them as individual objects. Any less than this, you can't see them. You will see them as a single object, yes. For this particular telescope, 200 mm telescope. All right, fine. Since we are low on time, okay, we will go to the last one, known as limiting magnitude or star magnitude limit. We will go to the last one, star magnitude limit. The faintest star you can see. So you have already learned about apparent magnitudes, absolute magnitudes, right? Right? Apparent magnitude, what is apparent magnitude? What is apparent magnitude? How bright the star appears to you, isn't it? Right? Now, how bright the star appears to you also affects how bright the star appears to you in your telescope. Okay? The telescope also has a limit. Now, if the star is anything less than a particular limit or a particular magnitude, can you see it? No, right? The telescope will also have such a limitation. So, The faintest star you can see in the scope is basically how bright or the least brightness or least bright object that you can see through a telescope. Okay. In order to calculate that, you call it limiting magnitude, LM. Okay. LM. And you say 5 plus oh yeah, means 5 plus 5 log D. Now you may wonder why this 5 comes. You may wonder why this 5 comes. Okay, the 5 is a standard value of a 1 centimeter telescope or 1 centimeter aperture. Okay, we always like to have standard values known so that you can use that to have further calculations. So the 5 is the limiting magnitude of a 1 centimeter aperture. All right. D is the aperture itself. What you saw earlier, the same thing, the diameter of the mirror or the objective or lens. All right. And when you do 5 plus 5 times log D, I am sure you will have calculators in that there will be a log, isn't it? So, 15.56. What did you even calculate, man? I didn't even see the question, no. The telescope has a aperture of 130 millimeter. The telescope has an aperture of 130 millimeter. Find the limiting magnitude. So what should you do? What should you do? Quickly, what should you do? The aperture is this, dear. 5 plus 5 times log 130. Now remember I told you 5 is the limiting magnitude of a 1 centimeter telescope. 1 centimeter telescope. And I am giving you the aperture value in millimeter. So here you have centimeter, here you have millimeter. What should you do? Convert what into what? Millimeter into centimeter. So it is 130 millimeter. How much? 1.3 centimeters. Is it? Is it? 13 centimeters, right? So what should you put here? 13. Now put that and see how much you get. 13. 13. Huh? Huh? Huh. Okay, listen. Okay, listen. Don't do this, okay? Don't do in your calculator, don't add this 5 plus 5, then multiply log D. This comes as a whole thing. Okay, you have brackets in your calculator. Either use that, okay, or calculate this first, 5 times log D, and then add 5 to it. What? How much are you getting? 10.56. Fine. 10.56. Okay. 10.56 is basically the limit your telescope can see. So anything fainter than 10.56 magnitude, your telescope is not able to see. All right. Fine. Yes. Log is a function, man. It's there inside. Yes. Okay. Yeah. What is his name? Vinith. Give him, man. Share. So, listen. The rest of the calculations, okay. Since you got an idea, the rest of the calculations you can do by yourselves, and you have all the formulas also. Okay. Fine. You can do by yourselves at home, and come tomorrow maybe. Yes. Can you do the calculations? The remaining calculations can come home or come tomorrow. I'll give you. Later I'll give you. First you have lunch. All right. So you know the basic calculations of the telescope, right? Yes. Now if I give you some telescope, any mirror, can you calculate and know everything of it? Yes. Good. That will be the end of. Any doubts? Doubts? Huh. 138. D. What do you mean D? 5 log D from the calculator. Look. D is given 130 mm. That question. Oh, okay. Listen, 1 centimeter on your scale. Okay. Say 0 to 1 centimeter on your scale. You have subdivisions on it, right? Okay. How many millimeters a centimeter? 10 millimeters is 1 centimeter. Yes. So 10 millimeters, 1 centimeter. What about 100 millimeters? 10 centimeters. 130 millimeters? Huh. 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 Say. Exactly. Because here this 5 is calculated for centimeters. You have to keep the unit same. Alright? The standard 5 is in centimeters. Yes. 200 mm telescope? Huh. 138, you mean this one? Okay. This is a standard value. It's a constant value. Okay. It is calculated something known as the Rayleigh criterion. Okay. It is basically once you calculate it for particular wavelength of light. So in this case, you are calculating in case of 500 nanometers, which belongs to green light. Okay. Once you do this, okay, you will get a value that is close to 138. I will explain to you after the lunch or during the lunch. Fine? That also I will explain to you. Fine? Alright? Anything else? Anything else? Done with calculations? Good. That will be the end of my talk. Thank you.